Drilling a well is a complex process involving 10 to 30 different service companies, each one adhering to stringent around-the-clock scheduling, safety, and environmental practices. Understanding how a well is drilled goes a long way toward understanding why producing oil and gas takes so much time and money. The first step in drilling a well is the planning phase. Members of the oil company's executive staff and senior exploration team meet to review information associated with a prospect and to get an understanding of the scope of work involved. Research and initial analysis is performed, taking into account lease options, potential reserves, risk factors, environmental concerns, and costs. During planning, the goals for the project are set out, including if and where to drill and the potential for field development. Geologists, geophysicists, and reservoir engineers begin by reviewing both public and proprietary prospect data. Mapping, well logs, and any existing seismic is evaluated to provide information on the potential of a prospect. Well logs are studied and interpreted to determine the presence of oil or gas in surrounding wells. Mapping shows formation structure, thickness, nearby fields, and well activity. Seismic, similar to an X-ray but using acoustic energy, is used to image or see the targeted area underground and can also verify information seen on other prospect data to determine whether a trapping mechanism for the hydrocarbons exists within the formation. Once a prospect area has been selected, the right to drill must be secured by leasing the mineral rights of the desired property from the landowner or mineral owner. In some cases, the landowner may no longer own the mineral rights. An experienced landman is needed to research deed history and negotiate leases. Once titles are researched, blocks of land are put together to create the lease area. An application for a permit, description of the proposed drilling program, a copy of the plat, the permit fee, an environmental assessment, water allocation, air emissions, and land use and disturbance must be submitted. Often, companies require additional information as they try to determine optimal locations to drill new wells. A 3D seismic survey is one of the most valuable tools used to gain a better understanding of the rock formation below. A seismic shoot is conducted by a contractor whose crew places lines of receivers called geophones on the ground to record the sound waves generated by a vibrator truck. The energy travels downward and is reflected back to the surface by the different rock layers. The geophones record the sound waves as they travel back to the surface. As the vibrator trucks move across the surface, new seismic lines are created. With the use of advanced software and powerful computer hardware, large amounts of seismic data can be processed. A geophysicist then interprets this information to create a three-dimensional view of the layers of rock below. Underground geologic features then become much easier to identify and target. This information gives other members of the exploration team new data to study. This allows them to map subsurface formations and anomalies and predict where oil or gas may be trapped in sufficient quantities to warrant exploration activities. This valuable data assists in the selection of drilling locations. Once a prospect has been determined to have potential, further studies are necessary. Geologists study logs from offsetting wells and construct various maps and cross-sections, while reservoir engineers determine potential reserves. When a prospect has passed the oil company's selection criteria, A drill site location is then selected. An Authority for Expenditure, or AFE, is prepared by a lease operator and sent to non-operators before work can begin. It is a budgetary document listing the estimated expenses of drilling the planned well. This estimate of costs requires approval prior to commencement of drilling operations. Once the survey has been completed, a stake will be placed where the well is to be drilled. Access roads are created so workers and equipment can get to and from the rig. The site will be cleared and leveled with a bulldozer. For support and permanent positioning of the wellbore, the cellar and conductor holes are dug and secured into place. The drilling rig and equipment are then trucked to the location, unloaded, and placed where it will be rigged up. A reserve pit may be excavated to capture drilling fluids, cuttings, and mud discharges so they can be recycled or properly disposed. Crew housing facilities, water lines, and electricity are brought in for 24/7 operations. After the rig is erected, equipment is moved onto the rig floor, assembled, and connected to power sources or pressurized piping systems. Some operators utilize an alternative method of managing return fluids and solids called a closed-loop system, which may reduce or eliminate the need for reserve pits. The closed-loop system separates the fluids and drilling solids by employing a series of linear motion shakers, mud cleaners, centrifuges, and collection equipment to condition the fluids so they can be reused or recycled. The solids or waste is properly disposed of according to state regulations. The hole for the surface casing is then drilled. A drill bit is mounted on the end of the drill pipe. As the bit grinds away, a mixture of water and additives called mud is pumped into the hole to cool the bit and flush the cuttings to the surface. The pipe and bit are then removed and surface casing is inserted into the hole. Surface casing serves to keep the wellbore intact, isolate the fresh water zone from contamination, and is the pipe to which the BOP and wellhead are attached. The casing is secured into place by pumping cement through the casing and the shoe at the bottom of the hole. This cement also acts as a barrier to provide a permanent layer to protect the freshwater aquifer. Next, the blowout preventer, or BOP, is installed on top of the wellhead before the drilling of the well commences. It is usually comprised of an annular preventer, blind ram, blind shear ram, and the pipe ram. The BOP unit's main function is to contain erratic downhole pressures, called kicks, and the uncontrolled flow of formation fluids quickly and effectively by sealing off the wellbore in several ways. If primary control of the well is lost during drilling or completion, one or more of the BOP's components are initiated to close across part or all of the hole to equalize pressures, thereby regaining control of the well. Without the BOP, this underground pressure can force the release of gases, fluids, and equipment, causing explosion, fire, and loss of life. Blowout preventers are critical to the safety of the crew, rig, and environment. At this point, using a slightly smaller diameter drill bit and pipe, the intermediate section of the hole is drilled through the wiper plug, shoe, and cement at the bottom of the hole. Once this section of the hole is drilled, the intermediate casing is set, cemented, and allowed to cure. Drilling then continues on toward the target depth. Millions of dollars can be spent drilling an oil well, so it is very important to gather as much information as possible at every stage to determine if it makes good business sense to continue drilling and complete the well. Drill stem testing, also known as a DST, is a procedure used on exploratory oil and gas wells to determine the boundaries and commercial productive ability of a hydrocarbon reservoir. Information gained from a DST includes fluid samples, reservoir pressure, flow rates, and formation properties such as temperature and permeability. As the well is drilling, the mudlogger takes samples and monitors incoming data. When the mudlogger has a good show indicating potential pay, drilling will stop and the pipe and bit are pulled out of the hole. The DST tool is then attached to the bottom of the drill string and lowered into the hole opposite the formation to be tested. One or more expandable seals on the tool, called packers, are initiated to seal off the zone. A hydraulic valve is then opened in the tool. Once open, the fluid then flows into the valve and up the drill string to the surface for evaluation. A typical test is comprised of several alternating formation flow and shut-in periods. Once the well has been drilled to its target depth, the drill pipe and bit are removed from the hole and a specialized logging crew and equipment are brought on location. The crew assembles a probe, which can be several different logging tools connected together. Each tool performs a different kind of measurement of the rock and fluid properties within the geological formations surrounding the wellbore. The probe is lowered down into the wellbore on a wire line until the top of the probe is below the target depth. The process is carefully monitored by the well logging crew and the geologist. As the probe is raised back up the hole, the various logging tools are activated by computers on the surface that produce a graph called a well log, which represents the geologic properties of the layers of rock. Lining up the logs, adjusting for variations in the surface elevation of each well, the geologist can get a good idea of the rock structure and possible presence of hydrocarbons across the area. Once the well has been logged and deemed a commercial well, the crew inserts the last string of production casing that runs the entire length of the hole and cements the casing in the hole. The cement fills the space between the production casing and the drilled hole, called the annulus. It also adds stability and strength to the pipe and creates a barrier between the formation and the casing. At the surface, the drilling rig is no longer needed. A coil tubing unit or workover rig is brought on location to perforate the targeted zone. A perforating gun is then lowered to the targeted zone. Pressure is applied to the coil tubing and perf gun, setting off a charge which shoots holes through the steel casing, cement, and out a short distance into the target formation. The perf gun is then pulled out of the hole. Stimulation is needed on most wells to establish production from the reservoir. Specialized equipment to hydraulically fracture or frack the formation is brought on location. Water, a small amount of chemicals, sand, and other proppants are pumped into the wellbore under extremely high pressure. When the mixture reaches the target zone, the pressure forces it out through the perf holes and into the low permeable shale, causing it to fracture or crack. This creates a fairway connecting the reservoir to the well. The sand and other proppants hold the tiny fissures open and allow the released oil to flow to the wellbore. This process is repeated in multiple stages to extend across the entire wellbore, with plugs placed between each stage to maintain pressure and get maximum flow results from the fractured rock. Once the fracking process is complete, the plugs placed between the frac stages are then drilled out to remove any restrictions in the wellbore. The frac fluid, also known as flowback liquid, flows back up to the top of the well along with hydrocarbons. The recovered frac fluid is treated and most reused on subsequent hydraulic fracturing jobs. This is done to conserve water and also as a cost savings measure. What is not able to be reused is placed in tanks and then trucked to be properly disposed. The production crew then brings in the workover unit and rigs it up to prepare the hole for production. The crew runs small diameter pipe, called production tubing, inside the production casing string. This serves as the conduit for oil or gas to flow up the well and adds yet another layer of protection to isolate the hydrocarbons from the potable water table. The next step is to install a permanent wellhead. Most wells at some point in their life will require artificial lift to get the hydrocarbons to the surface. In this case, a pump jack, oil storage tanks, and associated equipment are installed on location. As one of the many environmental safety measures, an earthen berm is built around the production equipment. During the production phase, oil is sent from the pump jack to the heater treater for initial processing. The function of the heater treater is to separate the oil from the water and gas. During this process, the liquids from the well are heated, the oil separates and floats to the top of the settling water, while gases break free and rise to the top of the tank. The gas passes through the mist extractor at the top of the tank and is sent to be stored or flared. The water is removed and stored for further treatment. The oil is sent to the storage tanks to await transport to the pipeline. During field development, additional wells are drilled on the lease to maximize recovery of reserves. Field development occurs in stages and includes many of the oil company's same teams of geoscientists and engineers who studied and evaluated the data to justify the initial well. Once executive management makes the decision to move forward, the planning phase begins. Next, additional drilling rigs are brought in, along with several service companies, to help with construction, build infrastructure, and assist the drilling company. An oil well can produce for 10 to 30 years during the primary recovery phase. Once production has declined, secondary or tertiary recovery methods can be used to extend the life of the well. When the well no longer produces at an economic rate, the final steps in a well's life cycle are abandonment and reclamation. The wellhead and associated equipment are removed. The well bore is filled with cement, and the well capped and marked. The area is reclaimed and the lease is relinquished back to the landowner. Oil and gas exploration and production is a complex but vital endeavor. The energy and products created from crude oil are endless and essential to our everyday way of life. Without it, roads, railways, and the skies would be empty. Construction, manufacturing, technology, and food delivery would come to a standstill. Oil and gas and the many technical and skilled people involved in drilling an oil well are crucial resources we are dependent on each and every day.